Thank you. This is third and probably the last lecture on the coherent potential approximation. We have covered various topics. We have even set up the the fundamental equation for CPA in the single band case. Before I begin, let me ask, are there any questions?
Yes, sir. So this is John.
Yes.
So we decompose the T matrix as summation over QI, right, last time?
Yes. Yes.
So I'm just a bit confused on like what's happening. Like, are we decomposing it on the based on the site, and it would look like, would it look like blocks in a like block matrices, or how would I visualize that those matrices if when we are decomposing it? So what would each
Matrix as a sum of site entries, individual site key matrices, correct?
yes?
Like what we did last time was we wrote T as sum over I, QI. This is a formal stuff. It has got nothing to do with anything else. I say I write it like VR. And I know that my T is the potential plus potential G0 T. This much I know. Correct? So I know therefore that QI is equal to small vi, the potential at each site, plus vi, G0. This T is the same as QI. So let me write it as J, QJ. So what is the question?
Now, can I visualize each of those QI as some kind of nearest neighbor interaction or something like that?
There is no nearest neighbor here. I'm just saying that I will write my T as a sum of QIs. This is an operator. There's not even a notion right now of that I'm going to take it in terms of near states. This is just a formal stuff. It's got nothing to do with anything else. There's no further physical meaning than just saying that there is a mathematical step.
Yes.
What is the question? And this QI naturally.
No, that's clarified. Like I was confused if there's some kind of physical interpretation to it.
Yes. Wonderful. Okay. Then the question that you asked was pertinent. Average of T is 0. I said is equal to average of QI equal to 0. You might argue that this is not quite correct. And I would like to submit that yes. If the probability distributions are additive, then yes. Otherwise, no. So take that to be an approximation. Further than that, you say that this QI is equal to some TI plus TI T0 Tj, where 1 minus delta Ij, and I is not equal to j, and then the successive summations are such that successive indices are not equal to each other. That's all. And then I say, saying that the average of T is 0 is in an approximation. This is exact. Average of T must be 0. The average of Ti is 0. That is an approximation. That's why it's called an approximation. It's a single site approximation. We are done with the formalism, so to say. What I would like to now submit that the operative equation, the starting point for the coherent potential approximation, would be the equation that I'm now going to write down. It is to say that the average of Ti is 0 and the average of Ti is B over 1 minus G0B. let me write this down. It is, you say, average of T is 0, which implies concentration of the A type of atom, and we are doing a binary alloy. It is V over 1 minus Green's function into V. What is V? V is to subtract off the sigma and you add epsilon A. This is the equation which is our operating equation, or which is the starting point of the equation of the current, of trying to explore the current potential approximation. This is the CPA equation for a single band, single site. I will have to make certain things explicit. What does this mean basically? It means that you have an effective medium, and on each side you have a sigma. So these circles means the on-site element is sigma. And then what you do is, over here, you remove that sigma, minus sigma, and you put in epsilon A. Scattering due to this, and the scattering due to epsilon B, if I were to take epsilon B instead of epsilon A, for an average must be equal to 0. That's what it means. You have a picture in your mind of an effective medium, okay, which is a faithful representation of the disordered system. And if it is, then this must hold. That is the condition that we impose. I can do a certain amount of, how should I say, a certain amount of massaging of this equation by taking cross product. I could multiply this with this and multiply this with this and set it equal to 0. Were I to do that, I would get, wait, I think I've already done it last time. Right? Have I done it or not?
Yes, sir, you have done it.
Okay. So, if I've done it last time, I'll just tell you how it is done, just to remind you. You take this, you multiply it by 1, and then the other term is just epsilon A minus sigma F epsilon B minus sigma. Multiply with this. Okay. So you have a term like CA sigma, CB sigma, and CA plus CB is 1. So you impose that condition that CA plus CB is equal to 1. The concentration of A type of atoms and the concentration of B type of atoms gives you 1. So it is a 50-50 alloy, it is 0.5 plus 0.5 is equal to 1. And similarly, by imposing this repeatedly, what you will get is that sigma this is what you do. Now, there are certain things I have to make very explicit for you. What is this F? This F is the diagonal Green's function corresponding to the effective medium. So F is basically sum over K 1 over Z minus sigma Z minus S of K. This is what this is. say, what is this S of K? S of K is the off-diagonal term, T. It is the band structure corresponding to the off-diagonal term. So, for example, in the one-dimensional case, S of K would be equal to 2T cosine K. Taking A, the lattice constant, to be equal to 1. So, what is that? S of K is just that. Corresponds to that. Supposing the bandwidth is 4T, you will write 4T cosine. So, here T square root of 3T is square root of 3T times cosine. That is what this term is. And this is the Green's function. This is the self-energy, sorry. So I can write this. If you have forgotten how to do it, please ask. But I will just write down the expression. I will write this as F0 or equivalent. Let me not write it like this because it looks rather foreign to you. I can write it as an integral rho of 0 z minus sigma z over, and just correct me if I'm wrong, okay, z minus y. I can write this. And what is this rho 0? What is this rho 0? It is the density of states corresponding to this. Now I will pause in case you have a question about this step. And this is actually equivalent to this. Any questions? Perhaps if you are still confused, when I take the example, it will become clear. So, but for our purposes now, just for further formal manipulations, what I have to tell you is the following, a very important thing. Sigma is a function of z. So if I have to be very correct and very clear to an audience, I would write this as sigma as a function of z. I would write this as sigma as a function of z. It depends on where you are looking. I mean, it is usually the on-site term like this, epsilon A or epsilon B does not depend on z. But in this coherent potential approximation and for a dissolved solid, it has to depend on z. Okay. So it depends on what is this f? F goddamn thing depends on z and it depends on sigma. As you can see, this is very clear over here. You basically have a nonlinear equation. You have sigma, which is on this side, but it's not a simple quadratic equation. There is another sigma sitting right here in the denominator. To solve this equation, what you normally do is adopt an iterative process to do some things which help you numerically solve it. Okay? Either a iterative approximation, or you can Rafson, or the trapezoid, or what should I say, the secant method, or the complementary Broyden method, and there's a whole slew of methods used to solve these nonlinear equations. Any questions up to this point? I just erase this F business. And let me say that I'm now going to put this equation in a more manageable form for analysis. So what I'm going to do is I'm going to define an average VCA value, which is simply CA epsilon A plus CV epsilon B. And I'm going to define a delta, which is nothing but epsilon A minus epsilon B by 2T. I mentioned this quantity delta, which is the difference of the two. If they are very different, it means that you have a strong scattering situation. If they are really close to each other, then you have something called a weak scattering. So depending on the strength of delta vis-a-vis T, the upping term, you define and do what is called asymptotic analysis of this equation. Just to make our life simple, I will set the 2t equal to 1. Then it is not too difficult for us to manipulate this equation and this equation to write epsilon A in terms of the VCA value, the virtual crystal approximation value, and delta. You can do that. Okay. And if you do that, how do you do it, for example? Let me say, how do I do it? So multiply this equation by CA. We have CA, say CB, let me multiply it by CB. So this is CB epsilon A minus CP epsilon B. Add the two. So CB epsilon B will cancel out. This will just become equal to what? CA plus CB epsilon A. So it is just epsilon A. And on the right hand side, you have VCA value plus CB delta. So I get epsilon A. Similarly, I can get epsilon B by subtracting. Lo and behold, what you will get here, instead of epsilon A and epsilon B, I will write it in terms of epsilon r, the VCA value, and I will write it in terms of delta. So I know that my epsilon A is equal to, let me put it here, how do I get it? I get epsilon r plus CB delta, and epsilon B is equal to epsilon r minus CK. Let's stick it in here. And I will work with this average value epsilon bar and the scattering value delta. Is this clear? So I will rewrite this equation. Explode this. Explore some limiting cases. At least one we should do. The second, I will let you work it out. So the case to do is say delta small, big scattering. Let's explore the big scattering limit in which delta is small. How many of you were there when I didn't, maybe I was in the first year I may have done this. But for example, if I want to solve a quadratic equation, perturbatively, how do we do it? Did I do it for you sometime in the first year? Yes, Saloni, did I ever do it? How to solve a quadratic equation if you don't know the solution of it? Be minus b plus minus square or b square minus 4ac by 2a. Did I do it?
No, sir. Means I don't remember.
Okay, so I just remind you. This has got nothing to do with the weak scattering limit. It's just what is called y example. I have a quadratic equation. Quadratic equation is ax epsilon x squared plus bx plus c equal to 0. Epsilon is equal to 0. Epsilon squared. Okay. And I want to solve that. But I don't know the solution. I don't know the solution to the quadratic equation, which, if I were more advanced beyond 8 standard, I would know. I would know that the solution is minus b plus square root of b squared minus 4 epsilon c over 2 epsilon. That is the solution. But I don't know that. So how do I go about solving it? I say first epsilon is equal to 0. In that case, my x0 is equal to minus c by 2. That is the 0th order approximation. I know how to solve this equation. I have been taught algebra in 8 standard, so I know how to solve this. Now I proceed. I say let x be equal to x0 plus epsilon x1. The next order is of order epsilon. Next order is of order epsilon, and I have to get this x1. But note that when you do this x1 itself cannot depend on epsilon. Otherwise, it will be order 2, epsilon square. So since I want to order epsilon, x1 has to be independent of epsilon. So what do? I stick it into this equation. So I have been told that a plus b the whole square is a square plus 2ab plus b square. And I have been told how to solve a linear equation. I don't do this. So stick it in. If you stick it in, you get epsilon into x0 plus epsilon x1 the whole square, that is this term, plus b x0 plus epsilon x1, that is this term, plus c equal to 0. Now when I know how to square things, so the first term is x0 square, so I have epsilon x0 square. Then the next term will be 2x0 epsilon x1. I can't keep it because I'll get an epsilon square term. That is not allowed. Third term is epsilon square x1 square. Can't keep it because that will be an epsilon cube term. So I just stop it. Bx0 plus epsilon bx1 plus c. But note, bx0 plus c is 0, so I can cancel off. And I'm left with epsilon, of course, has to drop out, and I'm left with an x1, which is equal to x0 squared, let me get this right, minus x0 squared by b, which is the same as minus c squared by b cubed. So the upshot of the process is that my first order approximation here is equal to minus c by b minus epsilon c squared by b cubed. That's what happens. Are you with me? You figured out how I've done perturbation theory without knowing the solution of the quadratic equation. Now, you can go back and check for yourself that if I were to make an expansion here, the first term will give you this, the second term will give you this. Okay, for example, all that you have to do is take this, write it as b 1 minus 4 epsilon c by b squared root. First term is b1. Okay, and then you expand this out. I can guarantee you that. Don't worry. If you don't, you come back to it. Is that clear? Or you want to do it right now? Why don't you do it? Check. I'll wait for 5 minutes. You getting this? Anybody else who gotten this? I think Akshat Vishwasan is getting it. Anybody else got this? Hmm? Yeah, m into m minus 1 by 2 factorial, that's all. And the square becomes 16, that becomes 1 by 8, so you get half to the factor 2. Okay, and then factor 2 cancels with this factor 2. Epsilon square cancels with epsilon to give you an epsilon. And c square by b4, and here is c square by b2. It all works out. So let us say we will get this. This is the kind of strategy that you use here. Okay, so let's continue. And I have you raise this and
Sir?
write. Yes.
So this is Chandrasekhar.
Yes.
So this perturbation method should work on any kind of equation, right? Not just restricting to quadratic, right?
Yes. This method is general, quite general. Yes.
Okay, sir. No, but do we know for sure if it converges to the solution?
Yes,
How
that
do we
is.
check for that?
You are getting epsilon, then you will get epsilon square, then you get epsilon cube. So epsilon is a small quantity.
Okay.
I've gotten a term with epsilon. The next one would be epsilon square. You can even go to the next order. You can work for the next order also.
Yes, sir.
So now let us take this. Let delta equal to 0. That's the first order. 0th order. So get sigma is equal to epsilon bar minus epsilon bar minus sigma f epsilon bar minus sigma. Yes or no? Well, I said delta to 0 here, delta to 0. Am I making sense? Ms. Saloni, how do you want to sleep?
Yes, sir.
You are in agreement with this step?
Yes, sir. This is fine.
The trivial solution here is, of course, sigma is equal to epsilon bar. Because if I set equal to this will go to 0, this will go to 0. So I'm done. Okay. So my first order term is just epsilon bar. And I will call sigma 0. Next order. And I take my sigma is equal to epsilon bar plus delta into sigma 1. Note that this delta is not operating on sigma 1. Delta is a small parameter. Delta sigma 1, the first one. Sigma 1 cannot depend on delta. Okay. So let us do this. So I get epsilon bar plus delta sigma 1 is equal to epsilon bar minus epsilon bar plus delta. Wait a minute, epsilon bar plus delta CB delta. Just give me a little CB delta. Minus sigma will be minus epsilon bar minus delta sigma 1 and here, iron bar minus CA delta minus epsilon bar minus delta sigma. Are we getting this right? Right. So what is cancelling off? Obviously, you say this will cancel off with this. This will cancel off with this. So I get delta sigma 1 is equal to, excuse me, minus 1. So let me put minus delta EB minus sigma 1 F plus delta square F E. Are you in agreement with what I have written down? Right? Yes, what about Sauganda? Do you get this?
I need a moment, sir. Just
Huh?
I need a second.
What did he say?
Still doing it.
He got it.
No, he's doing it.
He knows.
We have talked in the first part where you set delta equals to
You
0.
have to remove that damn thing. I can't hear you.
Then the first part where you put delta equals to 0.
Huh?
There you have two solutions, right? One is the sigma equals to epsilon bar, but you also have epsilon bar plus 1 by f. Because it is a quadratic in.
If I take epsilon bar equal to sigma, it satisfies.
Yeah, this is a solution.
Ah,
I say there is another solution because it is a quadratic in sigma.
There's a quadratic in sigma, yes. Okay, we can keep that. Let's remove it. Okay. Oh, that won't work. I will tell you later. That's not right. Just give me a minute. After I work out some. Is everybody getting this?
So why are we keeping that delta? We can cancel it on LHS and RHS, right?
Which delta? Here. The last
Delta sigma. Yeah, yes, sir. We can cancel the delta also, no?
Yeah, but are you comfortable with this, right?
Yes,
or
sir. Yes, sir. This is fine. I'm getting this. Huh?
not? Right? So I've done what you are asking me to do, Saloni. Exactly what you requested me to do. Or what you instructed, or what you ordered me to do. I've done this. Okay. So now this is not allowed because sigma 1 is depending on delta. What it means is that there is no first order correction. Now you have to interpret because the sigma 1 is coming out to be dependent on delta. And that means that, and that is not allowed because it has to be independent of delta. That means that there is no first order term. Now there must be a second order term. So I say delta square sigma 2. Let's see. Maybe there is no second order term either. We have to explore this. So I take a delta square sigma 2. This is what I do. Put it in, stick it into this equation. I get epsilon bar plus delta square sigma 2. That is equal to epsilon bar minus. Now I have to be careful and not make mistakes. That's the main thing. dB delta minus epsilon bar minus delta square sigma 2 F epsilon bar minus CA delta minus. Once again, some things cancel out. I mean, we don't give a damn. All this cancel. So I get basically the delta square sigma 2 equal to. Now I'm left with a delta. Yes or no?
Yes.
Correct. And I'm left with a delta there. Correct. So let us see what I will get. I have to be a little careful. Let's see. I get delta square PV minus delta circle 2. Is that right? F CA. Correct. Yes or no?
Yes, sir.
Thank you. I get delta square CACBF plus terms which are higher order in delta. Okay. The delta square CBCAF, and if you take any other term, you get a higher order in delta which will drop out. Okay, is that clear? So I drop out a delta square, I get sigma 2. Correction to this. Let me go back because there's not enough space here. So I'll go back here and say, and what is it that I have to do? I have to basically take this and say, okay, that my sigma of z is equal to epsilon bar plus CA CBF. That's this is, so this is equal to epsilon bar plus CACB. And what is this F? Sum over K 1 over Z minus S of A minus of sigma. Am I going too fast? Are you with me? Is everybody with me on this matter? Are we all?
Yes, sir.
Are we all? Yes. Okay. So if we are, then I'm writing it here. And first you pay attention, and then you can take down whatever you would like to. The sigma z is nothing but epsilon bar plus all of this. Correct? Minus delta square. Okay, I should have gotten that over a sigma 2 or something like that. Correct? That is what that sigma has to be. Correct? So I'm sorry, I missed out the delta square. Big mistake. Delta square again. But if I were to expand, if I stop here and I expand, okay, this delta square will come in the numerator and it will be a higher order correction. Okay. So I have to stop at this point. That is the trick. Like if I take that delta square sigma 2 and expand it out, like you take this common and do a Taylor type of expansion, I get higher order than delta, which I don't want because I want the second order approximation. I'm sorry, there's a delta square here which I missed out. So I basically have epsilon bar delta square CACF. Virtual crystal approximation. Is that clear? This is called Nordheim's correction. You remember, I made you work a little bit for the Bruggeman case. The Nordheim's correction is, this is the version of Nordheim's correction for the coherent potential approximation, as opposed to the effective medium tail. And it is symmetric. That is, you interchange this CA, TB. If you take epsilon A going to epsilon B, and vice versa, Okay, this delta square will not change because this delta is epsilon b minus, sorry, it's epsilon a minus epsilon b. Even if I make it the other way and I have a square term, it doesn't matter. I do this correction doesn't change because delta square goes to delta square. And CA goes to CA. So the VCA does something interesting. It doesn't give you a split band. Even if the delta is very separated and you get two bands, okay, the VCA will just give you one band. I don't know about the Nordheim connection. I think it will also not give you a split band. CPA. Is that clear? Now, what I would like you to explore, I will not do it, but I want you to explore it, is to say do the dilute limit. That is to say, you can do the strong scattering limit also, but let's not get into it. In the dilute limit, what you do is you take, say, for example, CA to be small, CB to be close to 1. Okay. And see again by perturbation expansion what is the kind of Green's function you get. What is the self-energy you will obtain? Very interestingly, what we will get, you wait time to do it, is that you get a Foster-Slater equation. So you get, for example, this delta, which is epsilon. Everywhere there is epsilon b. Notice, A is small and CB is large. Okay, so everywhere there is epsilon b. In one or two places, I remove this and put epsilon a. So this is the impurity. So you get this impurity potential 1 by delta is equal to n BCA. Something like this. I'll put a question mark. But you should be able to regain the Foster-Slater equation. I have not done it. I'm saying that you should try. Okay. I could go on and on about the Coherent potential approximation. I've done sufficient. Maybe I should just work out pedagogically, or at least lead you pedagogically to an example. Okay. So allow me to do that now. But before I proceed, are there any questions?
You would explain that why that other solution was different.
Because there again it's a second order term. I've not done it. I don't know. Yes, good question. All right. So allow me to proceed.
So could you please repeat Akshat's question? Johnson.
Yes.
No, could you please repeat Akshat's question? What Akshat asked, like we couldn't hear. What Akshat had asked, can you please repeat what he had asked?
What Akshat had said is I have sigma. This is very okay. So what I've said is sigma is equal to epsilon bar self-consistently this equation is solved. Right. So he says no, let me not do it like that. What I will do is there's a quadratic in sigma. I solve the quadratic in sigma. Okay, and I will get something. So solve it. So my answer is yes. You will not get a new solution. I would ask you to solve. I didn't do it. I didn't do anything.
Yes.
You can try it. Okay, so example. Let the free electron, let the density of states corresponding to the term 2T, okay, or the transfer term, be given by a semi-elliptic density of states. Be semi-elliptic in character. How does the semi-elliptic density of states look? This is 2 by pi, this is plus 1, this is minus 1. This is what is on the x-axis? Z. What is on the y-axis? Rho 0 Z. What is the semi-elliptic density of states? So I have rho 0 Z is 2 over pi square root of one minus, and therefore the Green's function corresponding to that, which we had worked out earlier, but just to remind you, 2 into Z. This is 2 by this is Z, this is Z, and this is 2. That's the Green's function corresponding. I just see if I've got some factor of 2 wrong. I do, then I have to correct myself. Where is correct? Where is it? Okay. So f of z is equal to f0 z minus sigma. Thank you very much. F of z is f0 z minus sigma. So this is equal to 2 into z minus sigma minus square root of z minus sigma the whole square minus 1. Correct? So now I get a relationship between f and sigma. How do I do that? I take this on the right hand side and I square it. So if I square it, what let us see, I have f by 2, actually I जाएगा minus 2, no 2 तो नहीं रहेगा, z minus sigma. And you square that damn thing, so it is z minus sigma the whole square. Correct? So I will simply get what? I will get some kind of a quadratic equation in sigma. If you simplify this, you will get sigma is equal to, I don't want to get it, equal to z minus h by 4. I think it's plus or minus 1 by f. This is what you do. Yes, this is what you do. There is nothing, this I can guarantee you. So, certain amount of progress has been made because of this very interesting property that the density of the Green's function of the effective medium is equal to the Green's function of the non-effective medium by a simple subtraction. Now what you have to do is stick this equation over here. When I stick this equation over here, you can see that I have sigma over here, I have a sigma over here, and there's an f over here. You will get an equation of the following type. So this is equation say 1. Let me call this equation main. Put 1 in main. And you will get the following equation. I'm not working this thing out. Neither have I worked this out. I leave it to you to work it out. You get an equation like f cube. I think I worked this out this morning. I sort of worked it out. F cube by 16 minus z x squared by 2 plus z squared minus delta minus 1 the whole square by 4 into f minus z plus epsilon bar equal to 0. You're still left with the epsilon bar, of course. Okay, and there's a delta. Somehow the CA and CB can be conspired to be thrown away, and you will get an equation like this. What is this? This is basically a cubic equation in it. How many solutions are there for the cubic equation? How many are there, Sauganda? We have a cubic equation, how many solutions? Yes?
And 3.
Three equations, after which 1, 2 will be complex conjugates of each other. Take that complex conjugate equation and you do the minus 1 over pi imaginary part of f. You get the density of states corresponding to the disordered medium as a function of delta and epsilon bar. So, what I want you to do is the following. Verify that you indeed get this equation, this cubic equation, and then solve it numerically for certain values of epsilon bar and delta, which I will give you. In fact, you can take epsilon bar to be 0 without loss of generality. You have to take solve it for delta equal to say 0.1, 0.5, 2, and 5, and submit it as a home assignment. This is a home assignment for submission. And I'm going to mail you this home assignment sheet. There are 2 examples of CPA being worked out. One is this one, which I have partly worked out for you. Please do not trust this equation 100%. I could have made a mistake. And the second one you have to do is for the one-dimensional density of states. CPA for a one-dimensional. Both these home assignments spelled out with all the I's dotted and the P's crossed. I'm going to mail it to you today. Okay. When do you have to submit it? 20 days from now. About 20 days. Thank you. Any questions?
Sir,
Yeah, Bolo.
this is Prithvi.